We know how to find derivatives, and antiderivatives just goes the opposite way. We know, for example, that the derivative of x squared is 2x. Therefore, an antiderivative of 2x is x squared. How do I write that? I could write it in words. An antiderivative of 2x is x squared. I could just write that out in words. But it would be nice to have shorthand symbolism. The appropriate shorthand symbolism involves what's called an indefinite integral sign. Oh, isn't that pretty? It's like an elongated S. In fact, Leibniz, who created this notation, thought of it that way for reasons I will not explain right now. If I write an indefinite integral sign, and write the function that is the answer for the derivative here, 2x, to the right of the indefinite integral sign, and also put a dx. Effectively, at the moment, what the dx represents is emphasizing to you what the variable you are integrating with respect to is. That's a mouthful. X. What's this d? Well, it's kind of related to the d's up there, but I don't want to get into details. What you write down here is the most general antiderivative. X squared is one antiderivative, but also x squared plus 1 is, x squared plus 2 is, x squared minus 17 is, x squared plus pi is, x squared plus or minus any constant is another antiderivative. If I just put a plus c here, where c is an arbitrary constant, maybe positive, maybe negative, maybe 0, I've got my most general antiderivative. C is an arbitrary constant. Indefinite integral symbols next to functions mean find the most general antiderivative. These two equations effectively mean the same thing. Two ways of saying the same thing. Now, you don't see any C's in the first equation. Well, I could have put a C in there. I could write d dx of x squared plus c is 2x because the derivative of a constant is 0. I could have written that. But it's, in a sense, such a trivial thing that we don't typically bother with the derivative statement. However, with the integral statement, if you forget the c, it's wrong. Because we want really a family of functions, infinitely many answers. We want to represent those infinitely many answers. Why? Because it's important in applications, that's why. For different applications, C might be different things. So you want to allow the C to be there so that you can solve for it depending on the application. Again, different applications, like, for example, in physics, if you're throwing a ball up in the air, letting it come down, hitting the ground, the C could be the initial height. And what is the initial height? It's whatever it is. Maybe it's up here, maybe it's down there. It depends on the particular situation. But you want to allow for it. That's important. In Calculus 1, your gateway exam is on taking derivatives. In Calculus 2, your gateway exam is on taking integrals, finding antiderivatives. This seems like a fairly simple one, but they can get much, much harder. Anti-differentiation is harder in general than differentiation, because there's often no clear way to guess. Here we can pretty much guess. There are other places you should be able to guess as well. We know the derivative, for example, of sine of x is cosine of x. Therefore, 3 dots means therefore, the indefinite integral of cosine of x with respect to x is sine of x plus c. These two equations are effectively equivalent to each other. They are two ways of saying the same thing. The derivative of sine is cosine. Therefore, the integral of cosine, technically an indefinite integral of cosine, is sine of x plus c. If there's an indefinite integral, does that mean there's a definite integral? Yes, but we have to wait for chapter 5 for that. Indefinite integrals are simpler than definite integrals. Indefinite integrals are just antiderivatives. Definite integrals in chapter 5, we will see, give you areas under curves. And, well, we use antiderivatives to find those, but the integral itself is not an antiderivative like this. It ends up being a number. Don't worry about that right now. More examples. Okay, let's just write down an integral. What's the integral of 1 over 1 plus x squared? I didn't write down any derivative fact, but you know some derivative facts. In fact, we just used one related to this 10 minutes ago. It's inverse tangent of x plus c. Yeah, we're using the fact that we know the derivative of inverse tangent of x is 1 over 1 plus x squared. If we didn't know that, how in the world could we do this? If we didn't know that, there's no way we could do that. But we do know this, so we can do that. But again, if you didn't know that, and you just look at that and say, oh, what's a function whose derivative is 1 over 1 plus x squared? You'd have no idea. I mean, maybe you'd guess something related to 1 plus x squared, maybe in the bottom of a fraction. It would be wrong guesses. Another example. What's the integral of 1 over x? Oh, natural log of x, right? Well, here we actually want to use that other fact related to the natural log derivative from last time. To allow for x to be negative, we want to include absolute value signs here. Plus c. And there is, well, we could say this is the most general antiderivative of 1 over x. That's actually a little bit of a lie, a fib. Is it a lie or fib? Well, it's an untruth. You actually can come up with a more general answer. More general answer is a piecewise function that's natural log of x plus some constant c1 if x is positive, and natural log of negative x, or I could write the absolute value of x there, plus c2 if x is negative. I could allow myself to have different constants depending on whether x is positive or negative. However, for almost all applications I've ever encountered, if not all applications, you've never needed to do this. So people typically just do this. And this affords me the opportunity of telling you a joke. This joke is on my YouTube channel. People seem to like it. What is the integral of 1 over cabin d cabin? Integral of 1 over cabin d cabin. People say, I don't know, or they say, oh, ln absolute value of cabin plus c, or then they say, wait a minute, ln, that's a log. Log cabin, I guess that's the joke. But no, it's not. It's not quite the joke. The joke is, the answer is houseboat. Because you forgot to add the c. The c. Houseboat. Okay. 1 over x is x to the negative 1 power. By the way, if you take classes from Dr. Yang, he's always wanting you to write jokes for him on exams. I haven't asked him how he grades those. There's a math joke you could write in an exam in the future if you take math classes from Dr. Yang. 1 over x is x to the negative 1 power. I wonder what in general the antiderivative of x to the n power is if n is not negative 1. If n is not negative 1. Let's see. Think about some examples. If we just integrated a plain old x here instead of a 2x, I guess the answer should have been 1/2 x squared plus c. If this were an x squared there, I guess if you think about it, it would have to involve an x cubed, maybe a 1/3 x cubed plus c, if this were x squared. We have to undo the power rule. Instead of subtracting 1 from the exponent, we have to add 1 to it. And instead of multiplying by the exponent, we've got to divide by it. If n is not negative 1, the answer is often written as x to the n plus 1 power divided by n plus 1 plus c. Check it. This is because the derivative with respect to x of, I'll put the dividing by n plus 1 out in the front as a multiplying by 1 over n plus 1. The derivative of that, not going to bother putting the c in there, I'd bring down the n plus 1, and I'd subtract 1 from the exponent. N plus 1 minus 1 is n, and then I divide the n plus 1s out, leaving me with x to the n. That's why this is true, but this can't possibly work if n is negative 1 because I'd be dividing by 0. So what if what if n is negative 1? That's the problem we did up here. That's the case where n is negative 1. Kind of weird. No logarithms there. A logarithm there. Weird, but true. Okay, there are plenty of other antiderivatives you should be able to write down. Let me just remark, you also should be able to have a little flexibility to do an example that might seem a little trickier at first. Let's do one related to this one. What if we wanted the most general antiderivative of cosine of 2x instead of cosine of x? Is it sine of 2x plus c? Well, that's what I'm starting to write here. But that can't be right because the derivative of this is not cosine of 2x. It's cosine of 2x times 2 because of the chain rule. Oh, that's easy to fix. Make it a 1/2 in front. Done. The derivative of this now is 1/2 cos 2x times 2 from the chain rule. The 1/2 and the times 2 will cancel to give you a 1. 1 times cos 2x. Be careful. Antiderivative of sine is not cosine, it's negative cosine x plus c. Yes, the derivative of sine is cosine. The derivative of cosine is negative sine. But an antiderivative of cosine is sine. And an antiderivative of sine is negative cosine. Tricky, but true.